Today, I would like to solve a particular type of problem. It is a problem that all students of physics are required to solve. This is important. I'm not doing any new physics today. I'm simply applying the physics that I already know to an interesting context. My strategy will be, and you'll observe me do it, to draw a picture, choose coordinates, draw a free body diagram, and write Newton's second law for both coordinate directions. That's how I solve all Newton's second law problems, no matter how complicated, no matter what forces are involved, no matter how strange the free body diagram. The procedure is always the same. I'm showing you this particular solution because it's a traditional solution of Newton's second law that all students are exposed to, and it gives us an opportunity for some really interesting problem solving. The problem that I have in mind today is known as the inclined plane. So I draw here a right triangle. You can think of it as a hill. If I wanted to solve the problem of a car on a hill, then it would be an inclined plane type problem. Here I've drawn this inclined plane, and I've drawn it as a right triangle with a certain particular interior angle, theta. We use that angle to indicate the steepness of the incline. A small angle, obviously, is a shallow incline. A large angle is a very steep incline. I would like to investigate the motion of an object, and here I'll just draw, like a crate, the motion of an object at rest on the incline, well, on the incline. And I would like to investigate this motion. A lot of things can happen. Particularly what I'm interested in is analyzing the motion of the box on the incline when it's at rest, or when it's moving down the incline at constant velocity, or when it's accelerating down the incline. You may think that I've just named all the different things that can happen. I haven't really, because there's another version of this problem where the crate is launched up the incline. That has a different free body diagram, so a different analysis. So when I analyze this system, I'm going to be specifically referring to it's at rest, or sliding down the incline at constant speed, or accelerating down the incline. This is the problem that I'd like to solve. So applying my Newton's second law strategy, I'm already off to a great start. I've drawn a picture of the box sitting on the incline. Now, the next thing to do is to choose my coordinates. But really, that's why I'm demonstrating this problem. Let's assume for a moment that I choose, as you might expect, the typical math coordinate system, with upward along the y-axis positive and to the right along the x-axis positive. Let's assume that for a moment, but you'll note I'm not writing it on my diagram. Draw a picture, choose coordinates, draw a free body diagram showing all of the forces that act on the object. Well, this object is on an incline, so what I like to do is draw my free body diagram with my square tilted as if on an incline. Sometimes students like to draw it flat. I'm okay with that. To me, it's aesthetically weird, but it doesn't hurt anything to do that. So now on this free body diagram, I'm going to draw all of the forces that can affect the motion of this block. Same as always, I'm going to go down the list of forces that I consider in my honors physics. That includes the weight, mg, directed downward. Anybody pushing or pulling on the block? No, but it'd be an interesting problem if I put Slim on the incline, pushing the block up the incline or down the incline. It would really add interest to the problem. But for the moment, no push or pull. There's no ropes attached, so there's no tension. Any surfaces in contact? Yes. The block is sitting on the incline, and so there is a normal force. Normal means perpendicular. The normal force is perpendicular to the surface of the incline. And so I draw it off at an angle like that, perpendicular to the incline. It's really important that I make myself comfortable with that because in just about every problem that I've seen so far, the normal force is directed upward, but that's because it's perpendicular to the surface that is horizontal. Now the surface is at an angle, and so the perpendicular force, the normal force, is at an angle. Is there friction? That's an interesting question because how do I know? Well, I know based on the motion. When I introduced friction, I had a block sitting on the table and I pushed on it and said, how do I explain this motion? There must be some force that resists the motion. We'll consider. If the block sits at rest on the incline, that's a little mysterious because I would expect gravity would cause it to accelerate down the incline. There must be some force that prevents it from sliding down the incline, and indeed, That's the force of friction, which I imagine would be directed up the incline. If the block is sliding down the incline at constant speed, that too is a little strange, because I would expect it to accelerate down the incline, not travel at constant speed. So there must be some force up the incline that impedes its motion. That would be the friction force, which I now even more greatly suspect is directed up the incline. If I see the block sliding down the incline and accelerating, but accelerating with an acceleration that is lower than the acceleration that I would expect caused by gravity, then there must be some force that opposes that motion. And so I'm really sure at this point that I can draw with confidence a friction force vector directed up the incline. Friction force opposing the motion of the block. Friction force doesn't always oppose the motion, but in this case, it certainly does. Any springs in the problem? No. So I've come to the end of the list. I've drawn a free body diagram. And I know that the very next thing that I'm going to do is apply Newton's second law to both coordinate directions. And I had talked about the possibility of y-axis and x-axis, but then I look at this and I think, oh no. The friction force and the normal force are not cooperating. Both the friction force and the normal force, they don't point just along the y-axis or just along the x-axis, but both. And so probably I'm in a situation where I should break those forces down into their components. If I choose to do that, everything will work out. Because the choice of coordinate system is arbitrary. How you choose coordinates doesn't affect the nature of things. But, as I mentioned before, the choice of coordinate system is arbitrary, and sometimes there are better choices than others. So I'm going to backtrack in my problem-solving strategy, and I'm going to choose a different coordinate system to solve the problem. And I can do that because the choice of coordinates is arbitrary. Instead of choosing the typical math coordinates, x and y axis, I'm going to choose a coordinate system that has two coordinate axes, one axis that is drawn parallel to the incline and points down the incline. I'll call this the parallel axis. And I'll draw that the two vertical lines, they mean parallel. And another coordinate axis that is perpendicular to the incline and away. I'll call that the perpendicular axis. So I'm not going to use the x and y axes to solve the problem. I'm going to use the perpendicular and parallel axis to solve the problem. Shadi, you just made that up? Yes. And I can choose any coordinates that I like. And why did I do it? Well, look what happened now. Now when I look at the free body diagram in this context, the normal force and the friction force are well behaved, because the normal force points entirely in the perpendicular direction and the friction force points entirely in the parallel direction. It points opposite. It's a negative parallel direction, but still, it's along that parallel axis. It's the weight force that is misbehaved now. So instead of needing to find the components of two forces, I need only find the components of one force. You say, well, that's not a great advantage. I'm comfortable with trigonometry. I'm perfectly happy to take the components of as many forces as you like. But there's an even greater advantage to this choice of coordinates. But I'm not going to see that yet. I'm not going to see that until I write Newton's second law for these coordinate axes. For the moment, my problem is that in the coordinate system that I've chosen, the weight vector is not parallel, it's not perpendicular, it's both. And so what I need to do is discover the parallel and perpendicular components. I'll draw in here dotted line. There is the parallel coordinate direction, and that's the perpendicular coordinate direction, and here is the parallel coordinate direction. The weight vector has a component that points perpendicular to, and apparently into, the incline. The weight vector has a component that points parallel to and apparently down the incline. But I'm not going to be able to draw those components or to determine what those components are unless I can figure out what angle I'm going to use. What is the angle between the weight vector in either one of those coordinate directions? I don't know, but I can find out. What I'm going to do is a little bit of quick geometry. And you may immediately object and say, oh, geometry's terrible, I hated that. All those proofs, all of those alternate interior angles are congruent, and betweenness theorems and all of that. I'm not concerned about that. I'm going to do a little bit of geometry, but I only have to do it once. So please follow along with what I'm doing and convince yourself what I say is true. You'll never have to make this argument yourself. So please just follow along with it so that I can convince you of a really important fact. I'm going to draw here on my original diagram a line that is vertical through the block. like this. I'm also going to draw a line that is perpendicular to the incline through the block, like this. Nice. Notice that this drawing has created a right triangle just here that includes the angle theta. I know that the sum of the angles interior to a triangle is 180 degrees, at least in a geometric sense, in a Euclidean geometry sense, which means that this angle is the complement of the angle theta. I'll call it alpha. The complement of the angle theta. That means they add up to 90 degrees. Of course they do. But I also notice that this line that I've drawn vertical through the block is perpendicular to the parallel of the incline. So I try to indicate there, it's difficult, that it's perpendicular. That means that this angle, which combined with alpha makes up 90 degrees, is the complement of alpha. Well, the complement of alpha is theta. What I've discovered is that on my free body diagram, this is the angle theta. It was important that I realize that, because now that I know that that angle is theta, it's possible for me to identify which component of the weight is adjacent to the angle. The weight is going to have a component that points perpendicular to the incline and inward, and it's going to have a component that is parallel to the incline and down the incline. Notice that it is the perpendicular component of the weight that is adjacent to the angle. Therefore, I use the cosine to find that component. Therefore, I use the sine to find the other component. So now I'll draw my free body diagram again the way that I would have drawn it from the start. I only drew it the first way for educational purposes. The way that I would have drawn it from the start is to leave the normal force alone because it's perpendicular to the incline and that's just fine with me. And to leave the friction force alone because it's parallel to the incline and that's just fine with me. But decompose the weight into its components. A component that is perpendicular to the incline, which is mg times the cosine of theta, and a component that is parallel to the incline, which is mg times the sine of theta. And I've heard throughout my career many complaints. So Shidley, I'll never be able to do that. I'll never be able to work that out. That was confusing. Well, if it's confusing to you, I suggest that you review it until you can convince yourself that it's true. But the fact of the matter is, for inclined plane problem solution, I only have to do this once. I only have to make this argument once, because from now on, anytime I do an inclined plane problem, the component of the weight directed down the incline is the sine component. And the component of the weight directed perpendicular to the incline is the cosine component. I need to memorize that. And in a quarter century of teaching physics, this is what has happened. Students have thought about this as, is the sine component of the weight that is directed down the incline. Sine incline, sine incline. Sine is sliding, or my personal favorite, sine is sin, and sin takes you down. All I need to do as a problem solver in physics is to remember that it is the sine component of the weight that is directed down the incline. And draw my free body diagram appropriately. Now, I have drawn a picture, I've chosen coordinates, I've drawn a free body diagram, so what I want to do now is write Newton's second law for both coordinate directions. But my coordinate directions are not x and y. They're perpendicular and parallel. I'll begin with the sum of all of the forces that act perpendicular to the incline is equal to the mass times the acceleration perpendicular to the incline. And suddenly I realize that my choice of perpendicular and parallel as the components, as the coordinate direction, smarter than I originally thought, because the acceleration perpendicular to the incline is 0. If I think about the perpendicular direction, the block is not going to accelerate on that axis because it's not going to fly off the incline. It's not going to dig down into the incline. It's only going to move parallel to the incline. It will not move perpendicular to the incline. The perpendicular acceleration is equal to 0. And indeed, the only acceleration in the problem is parallel acceleration. If I had chosen x and y to solve the problem, there would be an x-axis acceleration and there would be a y-axis acceleration, and my problem solution would absolutely work out, but it would be mathematically much more complicated. So I'm really thrilled. Let me get busy writing this. Sum of the forces perpendicular is equal to the mass times the acceleration perpendicular. So I'll look at my free body diagram and look only at the forces that are perpendicular to the incline. That is the normal force and the component of the weight mg cosine theta. The other forces are parallel. I'm not considering them yet. Only perpendicular forces. And because I chose away from the incline to be the positive direction, that means the normal force is a positive force and mg cosine theta is a negative force, and therefore the sum of the forces perpendicular to the incline will be the normal force minus mg times the cosine of theta is equal to the mass times the acceleration perpendicular to the incline, and that is the equation of motion for the perpendicular direction. I haven't even asked a question, but I now have an equation that can solve for the perpendicular motion of the block under any circumstances, at rest, constant velocity, or accelerating. This equation solves. The sum of all the forces parallel to the incline is equal to the mass times the acceleration parallel to the incline. Now I'll look at my free body diagram and I'll ignore those perpendicular forces. Consider only the forces that are parallel to the motion. Because I chose the parallel axis to be down the incline is positive, mg sine theta is a positive force and the friction force is a negative force. And so my equation of motion is that mg sine theta, a positive force, minus the friction force is equal to the mass times the acceleration parallel to the incline. And that is my equation of motion for the parallel coordinate direction. Wonderful. That is my Newton's second law analysis of this problem. The reason why I've shown it to you today is because you're going to have an opportunity to solve inclined plane problems of your own. So the skill of drawing a free body diagram in that context is really valuable. But since I've gone through all of the trouble of doing this out, I might as well ask a question, do a little solution on the end, because I can get something really interesting about that. I want to consider the case, just for interest. I want to consider the case where the block is sitting on the incline, but it's just about to slip. It's sitting on the incline and its velocity is 0, its acceleration is 0, but it's just about to slip. If the incline were just a little bit, the tiniest little bit steeper, it would slip and begin to slide down. So it's sitting there tense, just about to break free and begin to slip. But the velocity is 0 and the acceleration is 0. What will my Newton's second law equations have to say about that? The answer is interesting. I'm going to do two things to my equations of motion. Here, the normal force minus mg cosine theta is equal to the mass times the perpendicular acceleration. I'm going to realize that this acceleration perpendicular to the incline is equal to 0. So the normal force minus mg cosine theta is equal to 0. The consequence here is that in this problem, the normal force is equal to mg cosine theta. Not every problem, but this problem, yes. Because the perpendicular acceleration is equal to 0, the normal force is equal to mg cosine theta. You say, Charlie, I don't care. What do I care about normal forces? That's not what I want to know. Find me some acceleration. Find me something interesting. Well, because in the last lecture I realized that the friction force depends on the normal force, the normal force is now something that I really want to know. I need to know the normal force. I need to know how firmly the block and the incline are pressed together so that I can determine how much friction is acting in that situation. Because when I go to my Newton's second law equation of motion for the parallel direction, I see that it has the friction in it. So let me rewrite it. That mg times the sine of theta minus what I know the friction to be equal to. I now have an equation for the friction force, and I can plug it right in here. I'll replace the lowercase f with mu, the coefficient of friction, multiplied by the normal force. I make that replacement because I know that the lowercase f for friction is equal to the coefficient of friction mu multiplied by the normal force. F is mu times n, is equal to the mass times the acceleration. Notice that I dropped the parallel notation. I dropped the parallel notation because there's only one acceleration in the problem. I'm not going to get confused. That acceleration is the acceleration of this particular problem. But I had said that what I was trying to do was solve the problem of the block at rest on the incline and just about to slip, on the verge of slipping. But under those circumstances, the velocity is 0, the acceleration is equal to 0. And so the right-hand side of this equation is equal to 0. Well, Shidley, none of this matters because you don't know what the normal force is. Yes, I do. I discovered from my perpendicular equation that the normal force is equal to mg times the cosine of theta. So if I make that substitution into my equation, then mg sine theta minus mu mg cosine theta is equal to 0. Well, so what? So what? Something fun is about to happen. Mg sine theta minus mu mg cosine theta is equal to 0. Let me add this mu mg cosine theta to the other side of the equation. So that mu times mg cosine theta is equal to sine theta. I just added the mu mg cosine theta to the other side. So one is equal to the other. Oops. I'm getting funny looks from the audience, and it's because I wrote my equation wrong. Whew. Is that better? Good. So mu mg cosine theta is equal to mg sine theta. Look, there's an mg on both sides of the equation. I can divide both sides of my equation by mg, and the mg goes away. My equation is getting really simple, really fast. What I'm left with is that mu times the cosine of theta is equal to sine of theta. Now I'm really curious. I'll solve for the coefficient of friction. Mu is equal to the sine of theta divided by the cosine of theta. Wait a second, that's something special. The sine of theta divided by cosine theta is the tangent of theta. In this problem, where the block is sitting on the incline and it's just about to slip, it's not sliding. So this is a static friction situation. If I take the tangent of that angle, it's equal to the coefficient of static friction. So now I can go into the laboratory, or I can hire a bunch of people to work in the laboratory, and everybody get busy making inclines out of one material and boxes out of a different material, and setting up the inclines in such a way that it's just about to slip, measure the angle, take the tangent. That's the coefficient of friction. It's a way to experimentally determine what the coefficient of friction is between various substances. The coefficient of static friction. Because the situation that I've described here is a situation where the incline is such that the block is not slipping, but is just about to slip. So the coefficient of friction I found with this equation, mu, is equal to the tangent of... That coefficient of friction that I found is the static friction coefficient, not the kinetic. But I can devise an experiment that gets me the kinetic, because... Imagine that I change the angle of the incline such that when I put the box on the incline, it slides down the incline at constant speed. That is tricky to do, because once the box gets to sliding, it's going to accelerate down the incline. So I'm going to have to reduce the angle in order to get it so it cruises along at constant speed. That's a harder experiment to do than just finding out the angle where it slips. Finding the angle where it cruises down at constant speed is a trickier experiment to do. But when I do that experiment, I discover that the angle of the incline where it slides at constant speed is a smaller angle. And so I reanalyze with Newton's second law. If it's sliding down the incline at constant speed, what does the free body diagram look like? Well, it looks exactly the same. The weight components are the same, the normal force is the same, the friction is up the incline, but now it's kinetic friction instead of static. So my free body diagram doesn't change, which means my Newton's second law equation doesn't change, which means the normal force is still mg cosine theta. When I'm sliding down the incline at constant speed, the acceleration is 0. That's constant speed. And so my assertion here that the acceleration is 0 doesn't change, and my algebra doesn't change, and the result doesn't change. When an object slides down the incline at constant speed, the angle is a lesser angle. The tangent of that angle is the coefficient of kinetic friction. So today, I've learned how to appropriately draw a free body diagram for a situation where an object is moving on an incline, but also I've devised a way to experimentally determine both the coefficients of static and kinetic friction.